Don't get used to it. It's going to be cold front come through tomorrow quickly. Start out nice early morning, then it's going to go. No, that won't be ridiculous. And then it's supposed to be really nice this weekend. So, so I graded your tests. That makes me happy. I thought overall you did decently. You know, you saw the points that I gave you on the side. I think most of you who got points off just didn't do enough. In essence, you really didn't write enough. But what you wrote was actually pretty decent almost everywhere. Let's talk about a couple of things, though, that were the problems for me. It's this: why is it the warmest day of the year? It's warm because radiation in versus out affects things. I don't know why, and maybe you can answer. Why do you think that there is a time lag or a delay to warm up? A whole bunch of you said that. There's a delay to get warm. How fast is this radiation moving?
Instantaneously.
Speed of light, right? I mean, it's super fast. As soon as radiation hits an object, the temperature responds instantly. They're absorbing it, their molecules are moving faster. The temperature is. So there's no, it takes time. I assume that you found that somewhere on the internet when you said things like it takes time? Or did you talk to me?
No.
Zach, I think you got it. A couple of you got it right. How about the rest of you? Where did you find your information? Some of you had those cool graphs with the wave and everything, which is fine, but somebody speak, please.
I just got my information from the notes because I remember we talked about like the money with like income and outcome.
Yes, well, that would have been the good place to get it, but I'm assuming that some of you got it on the internet. I mean, it was open note. I don't care what you did. I mean, I don't care. I allowed you to do that, but what did you get? What did you get from the internet that seemed to give you the wrong answer? Don't all answer at once. I can only hear you one at a time. Isaac, did you get it right?
I was opening my test right now to see my grade.
Okay. Ryan, what were you?
I don't know. I'm having trouble finding my text. 1 second.
Oh, okay. So you guys are doing something on your computer. I don't know that. Lena, what are you doing?
I'm trying to pull it up, and this computer's super slow.
Yeah, your internet sounds slow.
Yeah.
Hi, Julia, what about you? Where did you get, because some of you, Aaron, did you get the graphs? No, I don't know if you did that one. Did you guys find it?
I think Aaron got the graphs, but I can't pull it up.
It's like I used ice fishing because the water has to get so cold, but then it also, like in the summer, it has to heat up, but that doesn't happen just immediately. So that was why there's a lag that has to warm.
Yeah, but it does happen immediately. As soon as you put radiation into it, the temperature goes up. It takes a long time to warm it up fully, but it will continue to warm up until the output of energy is greater than the input. There's no storage of anything. It's the storage that you talk about is called temperature. Temperature is how much heat the object has. So if the temperature is going up, it just means you're putting heat in, even though it's giving heat away. So it's all a balance between that. So that was a lot easier. It's only a 4-point question. And some of you I mean, I like your diagrams. It showed that there's a time lag in terms of temperature and warmest state, but I asked for the reason why that is. So that was one. The other one was just about the conversion of potential to kinetic, et cetera, in the atmosphere. Remember that the potential energy is based on the center of mass, which is 500 millibars. And I don't think anybody in class mentioned that. And I know that we talked about it in class. So you all got points taken off for the fact that you didn't reference it in terms of potential and kinetic energy of the atmosphere. And what's the final end of kinetic energy? Do you agree that the atmosphere eventually stops? Why? The atmosphere eventually stops. Why?
Is it like the center of mass is as low as it can go?
Well, yeah, I understand what you're saying, Zach, but I'm saying what causes the air to want to stop? Brian,
I'm not sure. Does it have to do something with the lapse rate?
wait. What do you mean? You all know this. What causes the air to want to stop moving? What causes anything to stop moving?
Oh, friction?
Right? Oh my gosh. You know this. There is a resistance to flow. Lena, do you remember what that is? There's a name for this resistance to flow in a fluid that is moving.
It was, oh shoot, I totally remember it too. It was oh my gosh. Viscosity, no.
Yes, that's it.
Yes, okay.
It's called viscosity. Have you ever heard of this word? Like ketchup is highly viscous. Water has low viscosity. So, but there's a resistance to flow. But where does most of the friction happen? Most of the friction happens near the ground. When air flows over rough surfaces, that's where it's slowing down. And if you didn't replenish, if you didn't replenish the energy, friction always uses up kinetic energy. But what's a better word than for uses up? Anybody know this word? Is that a good word? That's a good word. You should know this. Always usurps. It always uses up kinetic energy. So if you didn't replenish the kinetic energy, the atmosphere would stop. But kinetic energy is replaced. How is kinetic energy restored? PE gets converted to KE. But how do we get PE?
Raising the center of mass.
And then that gets potential energy. And what raises the center of mass?
Placing or having cold air above warmer air or more dense air.
Okay, well, if you did that, then you'd have a thermally indirect circulation. So you're not wrong, Zach, right? But in the atmosphere, what raises the center of mass of the atmosphere, which is 500 millibars?
Oh, would it be thunderstorms?
No? Remember we talked about the layer of the atmosphere from 1,000 to 500 millibars?
Wasn't it heating the air which causes it to go up because it expands?
Yes, so it's heating the air, right? Because then it would expand. So this would go up and the air gets thicker. Okay, well, we did this diagram. Remember that? Now, the question that I have for you then, Lena, is how does the sun heat the air near the ground? How does this happen, Isaac? How does the sun heat this air right there? What do you think? And Aaron, you got an answer?
Conduction and convection.
Well, yes. What does the sun do then, Aaron?
H-E heats the heats the ground.
It heats the ground. Then the ground heats the air through conduction. Convection moves the air up and down. It can also, how else could the ground heat the atmosphere?
You know. E.
Ryan?
Through the greenhouse effect.
Okay. So the earth gives off what kind of radiation?
OLR.
Long wave.
Long wave radiation, outgoing long wave, heats the air. What could absorbs it? Like you said, the greenhouse gases. And so that heats the air too. So, but that could heat the air up here, but it's going to heat a little bit more down here. And so do you understand that what I'm saying is that this atmosphere, this layer of atmosphere that I drew between, let's say, 1,000 millibars and 500 millibars will get larger the warmer it is. Okay? So what I'm saying is this distance is known as what we call thickness. Thickness is the vertical distance here. So then the question is, what are these lines? Before we answer that question, do you understand everything that's on this page? If I finished up some stuff, this would be through thermally direct circulations, converted to kinetic energy. Kinetic energy it's eaten up by friction. And so the energy goes to friction, and it goes to viscosity. And everything starts from the sun heating the ground through shortwave radiation. The ground heats the air through conduction, where it's transferred through the atmosphere through convection, or it heats it through outgoing long wave radiation. That air causes this layer to expand because warm air expands. It's thicker. But that raises the center of mass. The potential energy is then increased, which gets converted into kinetic energy through thermally direct circulations, which is just about everything else other than the ferrite cell. And then kinetic energy gets usurped going into friction. And this is the flow of energy throughout the atmosphere, all based on this idea. This is what eats it up. Now, do you understand that this is a layer? And if I heat the layer, do you agree it takes up more space? Okay. So there is something which we call the thickness relation, which states, right here, I'm going to say it to you, and I want you to say it 3 times. The thicker the warmer, the thinner the colder. The thicker the warmer, the thinner the colder. The thicker the warmer, the thinner the colder. Say it right now. Thicker the warmer, the thinner the colder. The thicker the warmer, the thinner the colder. The thicker the warmer, the thinner the colder. That's known as the thickness relation. It is also known as, more officially, Let me see if I can be a little bit neater. Oops. This is known as the hypsometric. That's its official name. So listen to me. Hypsometric thickness is the same thing. And it says the thicker the warmer, a layer, thinner the colder. Now, do you remember a long time ago? I gave you some information on the layers of the atmosphere. So do you remember, do you have notes on the layers of the atmosphere? This is like first couple of weeks of class. What's the lowest layer? What's the lowest layer of the atmosphere?
The troposphere.
And what do you know, what's the end of the troposphere called?
Tropopause.
And what do you know about the tropopause? What does it say? What fact did you indicate about the tropopause?
It begins at different points depending on where on the globe.
Okay, Beast, tell us what those are.
So the tropopause begins between 10 to 11 kilometers in height
On average, right?
on average. But at the equator, it begins at 15 to 16 kilometers, and at the poles, it begins at 5 to 6 kilometers.
Right. So does it make sense? Because the troposphere is the layer, and it's thicker when it's at the equator because it's warmer. It's thinner at the poles. That's the reason for it. But what I need you to say is, what are these green lines called? I'm asking you what this is called. Okay, so let me redraw them. And I labeled them 500 millibars. And this is 1,000 millibars. Now, what I'm teaching you today is hard. It's harder than the equations we had the other day, which we're going to get back to, okay? But because we started out in this interesting place coming out of the test, I want to show you how this relates. What are those green lines?
I could be wrong, but are they isobars?
Okay, so Lena says they're isobars. Is that correct? Aaron's saying no, or is that a yes? What do the rest of you think?
I don't think so. I think it has to be on a map to be an isobar.
Okay, so let's listen to what Ryan just said. Imagine that this is Illinois. Big Illinois, whatever, Illinois. And I've got lines on this map, and let's say it says 1,000 millibars. Okay, and then this line, let's make it 1,004 millibars. Do you agree that this is an area of low pressure?
Mhm.
So this line, that's 1,000 millibars, says if I walk on that line, the pressure one side is less than 1,000. The pressure on the other side is greater than 1,000. So when I walk on the line, every place on the line is 1,000 millibars of air pressure. So do you agree that if I walk this way, the pressure is going to go down? If I walk this way, the pressure is going to go up. So what Ryan said is absolutely true. Isobars, which are lines of constant pressure, are drawn on horizontal surfaces. So this way, what is that way? What is this way?
Vertical.
No, based on this map.
Mm,
Isn't that north? I mean, it's Illinois, right? It's north. What's that way?
South.
What's that way?
West.
West.
What is this way on this diagram?
Increase in height.
Right? Isn't that up? If you want to say increase,
Up.
that's fine. I think up's an easier answer, right? So what has to be this way?
Down.
What has to be there?
The ground.
Okay, so if I have the ground, we already know how to draw a ground, don't we? We draw a ground by a straight line with a bunch of these hatch marks. Remember, we've done this before many times. So those, like, if you were walking on this, you'd be walking this way. So if I pointed left, let's say that I'm walking this direction. Pointing left is which way?
The opposite way.
Okay. I'm walking on this green thing, which we still don't know what it is, but I'm walking this way. Which way is my left? Julia.
Like to the west?
I don't have it, no, because I don't have a direction here, so you don't know which way north and south and east and west is. I'm just walking from here over to this point there, right? I'm walking that way. So which way is my left pointing?
Like
Wouldn't,
you.
if we pointed straight at the screen, that would be going left.
Wouldn't it be pointing into the screen or into the board or however you want to think of this? It's pointing in, and then the right is pointing out. Now, I don't know what direction that is. I don't really care at this point, but just understand that to the left is into the screen. Now, what if I decided to turn left? Would I fall off this line? Because what is this?
It's a plane.
The line is actually a plane, right? So what I have is a plane that I'm walking on, right? Here I am, walking on this plane, walking that way. The only thing is, I'm looking at the side of the plane. So this plane, imagine that you had a piece of paper, right? Here's a piece of paper, and it looks like a piece of paper, but if I turn it to the side, if I go right on, do you understand that it becomes a line? So that's what I'm looking at. I'm looking at the cross section of something. Well, what kind of a plane is this? How would you describe this plane? What kind of a plane is it? Do you agree in this picture the blue ground is a plane? What kind of a plane is the ground?
Is it flat?
Well, yeah, so that makes it a what? Isn't that a horizontal plane? Or isn't that what I have up here? That's what I'm assuming. So this, when north is that way and south, what kind of a view is this? Which way am I looking at this?
Top down.
Okay, you could call it this, you could call it a top-down view. There's another way, two other ways.
Bird's eye view.
Okay, that's another one. I like this one, bird's eye view or a map view, right? That's what all these, it's a map. I'm looking from the top down. It's a bird's eye view. This is a what? This is known as a cross section. I'm looking at it from the side. So what kind of a plane is this green plane that I'm only looking at?
Also be a horizontal plane.
Okay, Zach says it's also a horizontal plane. And do you think he's right or wrong? Isaac, what do you think on that one?
Yeah, I think he's right.
In this example, it's horizontal. Right? I mean, they're all, do you agree that the green lines are parallel to the blue line? At least that's what I'm trying to be. But what's true about this plane when I'm walking on it?
It's only a limited area.
Well, it could go on forever, but what's true about being on this plane? Right?
I can't
That's
read
what I'm
that.
saying. Everything on this plane is the same pressure.
Okay.
Does that make sense to you guys? You know what we call that? We call that an isobaric plane. So when I'm walking on this surface, everywhere is 1,000 millibars. When I'm walking, if I walked up on this plane, do you agree that every place on this plane is 500 millibars of pressure? That's isobaric. In this case, they're the same as the horizontal planes. So if I'm over here, what's my pressure?
500 millibars.
500 millibars. I walk to this side of the plane and I end up over there. What's my pressure?
500 millibars.
500 millibars, right? But let me ask you this question. How far are these two planes apart there versus there? Answer?
Delta Z.
And? And do you agree that they're the same? They're the same, just because they're all horizontal, they're all parallel. Sure, of course, that's what they are. They're all parallel. Does that make sense to you guys?
Mhm.
So delta Z, what do we call delta Z?
A change in height.
No, well, okay, hold on. Delta Z is a change in height, but we don't call it that. What do we call it? Isn't that a thickness? It's the thickness of what?
Of the atmosphere.
Of
Of
the
those
atmosphere between two isobaric planes. So a thickness, write this down, is the vertical distance between two isobaric surfaces. I'm going to use the word surface rather than plane, but for now, plane is what you're thinking. Okay, now, where did you go? Okay, now listen to me. Do you understand what I'm talking about? By the way, have you noticed that I've not really used a whole lot of mathematics? Do you agree that this is a little bit harder to figure out because you have to conceptualize something in abstract visual space? But looking at this, how is your understanding of it right now?
4. Aaron says 4.
4. Okay, Aaron, good. 4. Ryan, you're at a 5. Isaac, Aaron at 5. Ryan, 4. Julia, 4. Okay. So, is there anything that you want to ask me about? Is there some, because here's the thing. I wish you guys were like, if I could ask one thing of you, it's just that you would respond with questions more and interact with me better. Because you just kind of sit there, so I don't know what you really get.
I have a clarification question. So we know that the isobars is what was on the horizontal surface plane, but then when you ask like what are those called, that's the isobaric plane. That's the name of them.
This is the cross section of an isobaric surface or plane.
Okay.
So you're looking at just the side of it.
Mm-hmm.
You're not looking at a line. It's just the side of it.
Okay.
Now, I want to show you something here. Okay, imagine that I'm going this way. I'm going this way. What's my pressure doing?
Decreasing.
It's decreasing from 1,000 millibars to 500 millibars. Do you agree with that?
Yes.
Okay. Let me erase this. I didn't mean to. Okay, so here's this. What if I drew this isobaric surface like that? Actually, let me do it this way. Okay? Do you agree that this isobaric surface is a plane that's now sloped?
Yeah.
Why is it like this? Why would it be sloped like this?
Would it be like the left side is warmer than what the right side is?
Over here, this is warmer than over here. Because the thicker the warmer, the thinner the colder. Do you agree with that? And that causes the isobaric surface to slope because the vertical distance between them. Okay, now let's try this. What is the pressure right here at the dot?
500 millibars.
What is the pressure over there?
Less than 500.
You agree? Julia,
Oh, more
Stop.
than 500.
stop. Julia, do you agree?
I think it would be more than 500
Why?
because like you're going from 1,000 to 500, so it
Right.
would have to be closer to 1,000.
If I were here, do you agree that the pressure would be 500? Air pressure is defined as the weight of the air above you. So I have 500 millibars of air above me. If I'm over here, I've got all this air above me too. So the pressure at that dot is greater than 500 millibars. And this pink line is horizontal. So what that means is that the pressure here is higher than the pressure here. And because this isobaric surface is sloped, that means there's a pressure gradient. The change in pressure over what? Over this distance. Right? That's the distance. What is this distance?
Delta X.
Over delta X. Does that make sense to you? What I'm saying is that there was the average temperature of this layer on the left was warmer than over here. If the temperature on average here is warmer than the temperature on average here, do you agree that I have a change in temperature over that distance? Did you follow what I said? Do I need to say that again? Do you agree that the average temperature over here is warmer, thicker the warmer, than over here? That created a temperature gradient. The temperature changes as I go from the left to the right. But do you agree that that set up a change in thickness? How do I write change in thickness? Do you agree that the thickness, look, it's thicker over on the left side, thinner on the right side? How do I write change in thickness?
Would be like delta delta Z.
It would be delta delta Z over delta X. But if I have a change in delta Z, don't I also have a change in the height of this green surface? So watch this. This surface is that high above the ground. This surface is that high above the ground. Are they the same height above the ground? Nope. They're different by how much? They're different by a change in the height. The change in the height indicated a change in the thickness. By the way, what would a change in the height look like if there was no change in thickness?
Would
Wouldn't it
it
just
all
wouldn't it look like this? Do you agree that there's a height change in the greens, but they're the same thickness apart? They're all just sloped this way? Okay, so here's what you need to realize is that I have a right triangle right here. I'm going to do it this way, a little bit thicker. I have a right triangle here. Do you agree that this hypotenuse that is sloped, right? What's the slope? What's the definition of slope? Everybody should say it like a response. What's the difference of slope?
rise over run?
Rise over run. What is this rise? What is this distance? That's delta Z. What is this distance? What is the run? Delta X.
Delta.
So do you understand this is the slope of what?
Of the isobaric plane.
I'm going to say surface, although you can think plane right now, that's fine. So what I have is a temperature gradient, creates a thickness gradient, creates the sloping isobaric surface. But what do you call delta Z besides the slope of the isobaric? Isn't this the change in something over a distance? What do you call the change in something over a distance?
A gradient.
What kind of gradient? In this case, delta Z.
A height gradient.
This is a height gradient, AKA, also known as a height gradient. Also known as, do you know this AKA? Do you know that? Okay. But because there's a height gradient, do you understand that means there's a pressure gradient, a horizontal pressure gradient. And that means there's what? I asked you a long time ago, what causes the weather? What's the answer you're supposed to give me?
The distribution of radiation across the globe.
Because,
The Earth's a sphere.
and how does this, how does the sun heat it? It differentially heats. It heats the equator more than the poles. If you heat it differently, what will that establish? A temperature gradient. If there's a temperature, there's a thickness gradient. If there's a thickness gradient, there's a height gradient, which is the slope of the isobaric surface, which tells me that there's a pressure gradient, which tells me the air is moving. That's the weather. This is known as the thermal wind, because what we're finally establishing is the link between a temperature difference and a pressure difference. And isn't temperature and pressure and thickness, which is density, aren't temperature, pressure, and density all related? And what are they related in?
Is it temperature equals pressure over density? Is that the equation?
No. What are they related in? What's it called? Aaron, you know this.
T H the what?
I don't think you're spelling. What is she spelling so far? I don't think that's right.
The something. You're not sure? So what?
Julia?
Okay.
I'm not sure.
Isaac?
This is
Oops.
the ideal gas law.
The ideal gas law. These things are related by the ideal gas law. Do you agree that this deals with thermodynamics, how heat and temperature work? This tells me how wind moves, and they're linked. This is how the weather works. Now, that's a pretty intense lecture so far. Do you think?
Yeah.
Okay, hold on to your hat for a second. I'm going to show you something here. Here is a map. And on this map, how is this map labeled? What are those black lines?
Isobars.
They are not isobars. Look at the upper left corner. What does it say the map's name is? What does it say up here?
Isotax.
Can you read it? It says, well, what's this? What's right there?
500 millibars.
500 millibars. Every place on this map is 500 millibars of pressure. So what kind of a surface is this?
Isobaric.
This is an isobaric surface. Every place on this map is 500 millibars. But what we're doing, this 5880 is what we call the height. It says I have to go 5,882 meters above sea level to reach 500 millibars at this point right here. How high do I have to go above sea level to go to this point?
5,820.
Can you read that all? Kevin, is that readable to you?
No, not at all.
Why can't you? Is it your eyes or Aaron?
Can you read it? No, it's just, the image is just too small for us on my laptop.
Is that bigger? I can only make it so. Do you see 588? No, here, what I'm looking at is look at the little box. Do you see where it says HDT?
Yeah, 5825.
Yeah, so right there, it's 5. Oops, no, wait, I can't do that because it changes where I'm at. Do you see that it says 5882?
No, we can't see it.
That little gray
It's
box?
just too small.
Oh, well, that stinks. How are the rest of you? Can you see that?
It's super small, but
Okay,
I somewhat see it.
let's do this. Go to this link. Okay, I sent it in chat. Just click on that and it'll take you to this page so that you can all open a window to it. Okay, then where it says, see what it says is NAM? Just go ahead and click on that. And then over here to the left, see it says 500 millibars? Click on that, it opens this menu. And then click on the one that says wind speed.
Okay.
Okay, and it should take you to this picture. So on this line, it says 5880. You see it now?
No, because on our computer, it's still too small. Let's see. I can't make it any bigger.
Are you on like a separate window or something, or?
No, it's in the screen. I just cannot make it any bigger.
Do me a favor for a second. Hit Control-0.
Control-0?
Yep. That changed anything?
No. Let's try it again.
Well, Control-0. See, when I hit Control and I use the up mouse key, it zooms in like this. You can make it a little larger. Control 0 just resets it to the correct size.
I'm still not doing anything.
How big is your window? Is it taking your whole laptop or?
Most of it
Okay.
is just not, it just will not be any larger.
Well, when you click on the little box, can you read the little box there then?
No. It's about a half an inch across. It's just too tiny.
Oh. Well, copy that link and maybe look at it. I mean, but here's the thing, right? So you're just gonna have to take my word for it then. How are the rest of you doing? Are you here? Okay. So 5880, and then over here it's 5820, right? This next line. So these lines are all what we call iso heights. They're lines of constant height. And a line of constant height says, how high above sea level do I have to go to reach 500 millibars? And so what I'm doing over here on one line is I have to go up 5,880 meters. And over here, I only have to go up 5,820 meters. So those lines are 60 meters across different. When I go from, okay, now watch. I'm going to go. When I go from here to there, that's a delta Z of 60 meters. Does that make sense? Over that distance. So there's a height difference, 60, but it's over this horizontal difference. So what that tells me is this. I'm going from 5,080 to 5,820 or 5880 to 5820 meters over that distance, delta X. So what I really have is delta Z over delta X. And I'm telling you, that means that there is a pressure difference, that these two are related. Now, do you agree on the left side of this diagram, over here, the isobaric surface is high up. Over here, the isobaric surface is lower. There's a height gradient. It's higher heights to the left, lower heights to the right. But I also said that there is a higher pressure to the left and a lower pressure to the right. So what that means is high heights to low heights is the same thing as high pressures to low pressure. So I'm going to erase this. Do you have any questions before I erase it?
No.
I'm going to go back to what we did before. That we have two lines. And this time it's, this line is some pressure. That's some P plus delta P. And this is a bird's eye view. So that is north. If that's the case, I call those isobars on a horizontal surface. But what if I had called them Z? What if I pretended that was a iso height on an isobaric surface? Then what would this iso height be?
Z plus delta Z.
If this way is a higher pressure, which it is, then that way is a higher height. So I could use this as a height gradient. Or I could use it as a pressure gradient. And the question is, how are they related? How do we convert from pressures to heights? And I'm going to tell you something pretty cool. But I want you to think about what I'm saying here. Do you agree if, now so here, I'm going to clear this up. Maybe this is confusing to you. So I'm going to try to clear this up. I either use this, I would use iso heights drawn on an isobaric surface, or I would use isobars drawn on a horizontal surface. It's this or this. What I'm telling you is that it tells me the same information. If these two lines are closer together, what does that mean?
Wouldn't that be like higher wind speeds?
Well, it would, well, yes, but before you go there, if I brought those two lines together, what's bigger? First of all, what's smaller?
The change in pressure and the change in height would be smaller.
No. The change in pressure and the change in heights are the same. Delta X is smaller. The distance between them is smaller. But do you agree that the pressure gradient would then be bigger? The height gradient would be bigger when the distance between them is smaller. So if these two lines were closer together, I have a stronger height gradient or I have a stronger pressure gradient. But the thermal wind says they're the same thing. Let me show you one more thing. Notice in the upper atmosphere, I use iso heights because every place on here is 500 millibars. So these lines all indicate height. I go to 850 millibars. Same thing. 850 millibars, those are how high above the ground do I have to go to reach 850. But when I go to the surface, those are isobars. Isobars are on the ground, which is considered horizontal, at least sea level. But higher in the atmosphere, I use iso heights, and there's a reason for that. Let's look at this. Let's imagine that I have this. What is that?
So the ground.
That's the ground. What is this?
Parcel.
So imagine that I take a parcel of air and I put it into the atmosphere. And I let go of it. Do you agree that that parcel could stay there? So let's just imagine, even if it doesn't stay there, initially it's I let go. What's its initial velocity?
0.
Right. Are there forces acting on this parcel?
Gravity.
Okay, so gravity is trying to pull it down. Any other force? What's air pressure defined as?
The weight of the air above us.
Isn't there higher pressure down here and lower pressure up there? Isn't there a pressure gradient force? Which way does air pressure, which way does the pressure gradient force point? Rule number one.
Some high to low pressure.
Do you agree? It wants to push the air going up and gravity wants to pull it down. So this is gravity, right? This is gravity going down, pressure gradient force pointing up. What does the equation look like? Give me the equation. Who wants to try to read it for me? Isaac, can you do it?
The equation on the left.
Based on this diagram, what does the equation look like? What's the pressure gradient force?
The change in pressure. Over gravity.
No. Lena?
Yeah, wasn't the pressure gradient force? It was like -1 over density times dp over dx.
Well, okay, if you want, I could use D, right? Does it matter? Over dx?
Oh yeah, over dx.
Do you agree? Is that what's showing in this diagram? That the pressure changes as I go? Which way is dx pointing?
Oh, so it'd be dz.
So it would be dz. What's it balanced by?
Gravity.
Right? There's a name for this. It's called hydrostatic. Remember we had this, just reminder from last week. What's this? What is this force?
That's the PGF.
Now be more specific. What kind of PGF is this? Isn't that the horizontal PGF?
Yes.
What kind of PGF is this?
That's the vertical.
Right. And what's this force?
That is the... Isn't that the centrifugal force?
No.
And
No, not 2 omega v sine phi.
no.
And help her out, guys. What is that, Julia?
Coriolis force.
That's the Coriolis force, right? So CF is Coriolis force. So the horizontal pressure gradient balanced by the Coriolis, what's that called? What's this equality called? Brian? Go ahead, Zach.
Oh, geostrophic.
This is geostrophic. This is the vertical pressure gradient force balanced by gravity. That's called hydrostatic. Follow? You think these things are important? I think so. Okay. So I want you to see something right here, though. So what I'm going to do here, watch, guys. I'm going to use delta just because I can do delta, right? Delta or D doesn't make a difference, really. One is the instantaneous, one is over a distance. I'm talking about planes, they're apart, whatever. But watch what happens if I group it like this. All I did was multiply through by delta z. Does that make sense to you? So I take the hydrostatic and rearrange the terms. And what if I divide both sides by delta x? What does this become? What is this?
You know? What? G, E, G, O, G, O.
What have you got, Aaron?
She says geostrophic. Is there more to it?
Well, no, I'm just looking at inside the box. What do you call this inside the box? See, I took the hydrostatic, I changed it a little bit, and now it's over here. So this is just the what? What's inside the box?
PGF.
What kind of PGF? Be more specific.
Horizontal.
This is the horizontal pressure gradient force.
Okay.
What is this on the right? Isn't this a height gradient? Times what? Times gravity. In other words, look at the question that I asked you. I said, how do those things relate? Well, they relate because this one needs to be multiplied by 1 over rho, and this one needs to be multiplied by gravity. So when I'm in the atmosphere, which do you think is easier to work with? Density of the air or gravity? What's easier to deal with?
Gravity.
Gravity, because what's gravity? Well, it's a number, right? It's 10 or 9, 10 meters per second. What is density in the air? Well, doesn't it depend on what the pressure and the temperature is? Because the ideal gas law. So if I wanted to know the true strength of the pressure gradient force, I need to know the density. But if I don't know the density, or I don't have to deal with it, all I need to do is a height gradient multiplied by gravity, and that's easy. This thing here on the left, this box here, is horizontal pressure gradient force. They're the same thing. The left and the right are the same thing. The only thing is, I need to know the density on the left, and I only need to deal with gravity on the right. So when I look at this map, I say there is, there is a pressure gradient force that points from high heights to low heights. There is a pressure gradient force that points from high heights to low heights, and that is balanced by the Coriolis force. So that these isoheights, the closer together, the stronger the winds. In the upper atmosphere, we use heights. At the ground, we use pressure. You know why? Because at the ground, I measure the temperature every hour. Right? That's what a station plot is. Give me the pressure, give me the temperature, I can tell you the density. But in the upper atmosphere, I know how high it is. I don't necessarily know the temperature all the time. And it's easier to use gravity. Okay. How are we doing on this? Now, here's the problem I have. So yesterday I had a a workshop or something, some person came and talked about online classing, so there's no such thing as lazy students. Do you agree with that? How many, on a scale of 1 to 5, 1 means you are absolutely the hardest working person ever. 5 is I'm really lazy. How would you rate yourself? Isaac, what do you say?
I feel like I'm a pretty hardworking student.
Okay. Aaron, how are you doing?
She said 3.
Okay, so those of you who said 3, or Julia, you said 4, what does it mean to be lazy? Why are you lazy? This is just curiosity. I really want to find out just from you. Okay, so we're gonna give your brain a little bit of a break. What makes you lazy? Why do you think that you are, Julia?
Honestly, like I kind of just do the work because I have a deadline instead of like trying to actually go out and learn as much as I can. It's more like, let me just get the information that I need and send it in.
What about you, Ryan?
I don't know. I wouldn't say like that I'm lazy, but I do most things on time. So maybe closer to a 2, I guess.
Zach, how would you define what a lazy person is?
Like for me, like I think I'm lazy because it's like I try to push stuff off until the deadline because I know I work better under pressure. So I don't know if so it's like more like I don't know, I guess it's like someone who waits for like the last minute or like just does as least
You do the
quality
least
work as
amount of work
possible.
as you need. Is that what
Yeah.
you're telling me? Well, if I define lazy that way, is that you?
Well,
Everybody else, do you do the least amount of work necessary? Does that make you, do you think that makes you lazy? I'm just curious. I'm not mad at you at all. I'm just trying to figure out if there's such a thing as a lazy student. I've seen lazy students. I've seen students like, why aren't you doing any work? I don't feel like it. Right? Because how busy are you in your life? What's your rate from 1 to 5 of busyness? 4? What do you do, Julia? 3, 4?
Well, right now I feel like I'm pretty busy because I'm working, and then also like I also sometimes go and babysit my cousins because my aunt works a lot and she's like getting a divorce, so that's kind of messy. But also I'm going to Illinois State in the fall, so I'm like every day I've been like calling with people and meeting with people about getting my stuff transferred and then trying to figure out what else I need at COD, and it's just kind of been crazy for me.
How busy are you, Isaac?
I'm not really sure.
You don't know how busy you are?
I mean, I guess it just depends on the day, really.
See, I would say what I see problems with students is that some students are lazy. And to me, a lazy student says, I don't feel like doing it. I'm sorry, I know lazy students. Why did you do your assignment? I didn't feel like it. I played games, I played on video games or whatever. Now, do you agree that you all need to play? You all need to have some relaxation time. So that's not making you lazy. But if you're like, I need to do my homework and I don't feel like it, I'm lazy. I need to exercise and I'm not going to exercise. That's lazy. Some people are busy. They're like, oh my gosh, I have so much going on right now. Some of you are too busy which means you don't prioritize school. So what's your biggest issue to be successful in school? I would say time management, right? It's time management. Some of you are lazy. Some of you, what's your scale of don't you have to answer this? What's your scale of motivation? Are you motivated to learn? Now, I agree that some of you, and Julia, you were very honest, like sometimes I just get a deadline and I do the work because I need to make the deadline, rather than going, oh, I really want to learn this. That's a true statement that people do that. Some of you are like that. Do you agree that you are, how many of you are like deadlines because it focuses you to finish on time? Do you meet deadlines? Do you think this semester would be easier if I just said turn it in eventually? How would that treat you?
Well, like I'm taking a humanities class and I have to have like 4 assignments done every 2 weeks. And I feel like even having 2 weeks is too much time. Like I like, hey, have this done by like in 3 days or a week. But like
No, that's because Lena works ahead a lot. Do you ever have a struggle making the deadline? Would you like a teacher to be compassionate and let you turn it in late, or just penalize you and say, no, I'm sorry, you missed the deadline, it's done? What do you think's better for you? How much your opinion?
I mean, better for me because like I work better under pressure, but sometimes it's just like, so I was like, sometimes I do just procrastinate. I do it in like the last couple days because I know like I work better under pressure, but like sometimes I just underestimate how much work it really is and how much work it's going to be. So I'm like maybe a couple days behind on something, so I'm like, that's just like my fault. And like if the teacher doesn't want to take it, like that's fine because it was my fault in the end. But it's definitely nice when they do take it.
Okay. What do you think, Isaac? What's your thoughts on this?
I mean, for me, I think I usually get my assignments in on time, but sometimes when I don't, it is nice if the teacher will just wait an extra day or two and then I'll get it in.
Does anybody resent that you did all your work on time and somebody gets the benefit of the doubt? Does that bother you? That somebody else is getting the same grade that you did, even though they turned it in late? I just kind of want to know your opinion. That's your opinion, right? Either you are upset sometimes or you have some upsetness. Lena, what do you think?
I feel like that's so situational because like if someone had something happen or going on and they got the same grade if they turned on late, like okay, but I don't know about the other hand. Like if they just blew it off and then
Because they're procrastinators, right? So I mean,
don't know.
Here's the one thing I know about students is that there's one size doesn't fit all. And sometimes somebody needs a carrot, sometimes somebody needs a stick, sometimes somebody needs some mercy, sometimes someone needs to pay the price of their errors, right? The consequences. If you don't get consequences, you never learn to be. Here's something that's really good. If you're in a marriage relationship or something and you're living with somebody or whatever, and let's say that the other person leaves socks on the floor. They come home from work and they leave their shoes on the ground. And you go over there and you straighten them up. What are you teaching that person?
That behavior is okay.
That behavior is okay and that you're going to take care of it. And then what's that person going to do over the course of 2 or 3 years? They're never going to put away their shoes. This is what your parents do, right? Put away your clothes. But then how many of you have a parent who says, put away your clothes, you don't, and then they do it anyway? You don't think kids learn, I don't have to, mom's going to do it, dad's going to do it, right? So I look at that and I think this is what we need to do. So I always have to run the risk of, do I penalize you for being late, or do I make sure that it's on time, or do I give you some mercy? I don't know. I wish you were motivated. I wish you would independently just say, I'm going to do it. That makes teachers really happy. So I don't know. That's just something I'm thinking about. So here's what I'd like to see with you guys in this class. Am I still sharing my screen? Yeah. I want you to tell me what this is, because I don't think you understand this as well as I want you to understand it. So how would you summarize this?
Like that final equation of.
No, Zach, I want you to kind of tell me, what have we talked about since the beginning of class today? Once we got past the sun heats the ground and we talked about those layers, I want you to tell me what we've done. And as a class, let's just have a conversation. But I need everybody to participate and think about how you're going to contribute to this.
So I think for the most part, we definitely tied in a lot of the stuff from unit 1 to what we're currently learning with like different types of wind, like the hydrostatic and geostrophic. And the main thing we learned is that a change in temperature over some distance can affect the winds through various means, with like changing the thickness over distance, and that in turn changes the slope of the isobaric planes. And since there's a slope difference, that means there's also a pressure difference, which would change the winds and make the winds want to move from the high pressure to the low pressures.
Now let's stop for a second on what Isaac just did. What did you think about what he just said, and that he took that statement? It was kind of impressive, wasn't it? Mm-hmm. And I think, Zach, this is why your essays tend to be pretty decent, because you have that ability to do it. What I would love to see from you is for you to formalize that, because the way what you just did was really good. I'd like to see how great it could be. And I think that's what you could practice before a test, or you could practice, because my essay tests are take home. You have more time to devote to it. But let's start with a few things in conversation. So Zach initiated. He said, well, we talked about the hydrostatic and the geostrophic. So let's just break it down from there. Talk to me about what these things are. Which one do you want to start with? So somebody else try a conversation with us. In fact, I want a conversation. You know what I mean? Conversations require talking.
So would you guys like to start with the geostrophic? Is the hydrostatic kind of builds off that?
Mm-hmm. Tell me about what it is in your own words, right? Own it. Own it. Let's see if you can own it and then make it better. So if Kevin, if Erin's got something that she wants to say, if she can kind of talk to you, and then you can say it for everybody, because I'd like to include her in that same discussion.
That's what he said, start. You? I don't know what you're saying. Other ones as well.
So give me what is it? What is geostrophic?
Are we talking specifically wind or the geostrophic balance?
Okay, the geostrophic balance, Lena, is just an equation. One term on the left, one term on the right. They're represented by arrows, right?
Mhm.
But the wind responds to that. So talk to me about what the air is doing, right? This is all about air moving. So what does it mean when the air is geostrophic or when the wind is geostrophic? What does that mean?
So isn't the wind is it gonna be curved in geostrophic? Like there's a area of low pressure in the middle and then it's high pressure outside of it.
Okay, wait, which case was geostrophic, Ryan?
Case 2.
No, geostrophic is case 1. What do you call case 2?
Oh, sub-geostrophic?
Yeah, but I don't even know if I gave you this word. It's in the notes, but what is case 2 generally called?
Was it the curved upper level flow?
And there's a name for it. Like what's case 1 says linear upper level flow, which is geostrophic. What do you call curved upper level flow?
Gradient.
It's called the gradient wind. Now don't confuse that with pressure gradient. It's just called the gradient wind. I don't know who made up this name. I think it's a stupid name. I wouldn't have called it that, but I don't get to make it up. Somebody else did it and we just go, okay, whatever. I don't believe in changing language to fit things just because, but that's called the gradient wind. So I want to focus on the geostrophic wind. So Ryan, if that's the case, what's the first thing you need to talk about?
So for the geostrophic wind, I know it has the PGF and the Coriolis force. Oh, and is it just two parallel isobars, one with high pressure and one with low pressure?
Sure. See, I think maybe this is where you guys are hung up on stuff. I am a scientist. I have to learn all the details. I need to know it up, down, left, right. And I do know it. I know this stuff. I can change it with anything. I can see how people manipulate, whatever. I can do this because I have experience on it. You are in an introductory level class, and I've given you some hard concepts. But what I want to do is I want you to dumb it down. And when I say dumb it down, that's actually kind of a bad word. I want you to explain it so that somebody understands what it is. So when I dumb things down, what I tend to do is I speak in simple terms, things that everybody can understand. I use personification in air. Do you understand that air is not real? I mean, it's not like human, it doesn't live. But if I personify it, what I do is I give it human characteristics. So I'm going to start with this really simple. What makes air move? And I'm going to say it wants to do something. What does it want to do?
Move from high pressure to low pressure.
So the very first thing is air wants to move from high pressure to low pressure. Okay, that's what it wants to do. Now, if we wanted to be more college educated, if it's going from high to low pressure, do you agree there's a difference in pressure over a distance? But that is actually called a what? What's a change in anything over a distance?
Gradient.
That's a gradient. So when I have a pressure gradient, then the air is going to start to do what? Move from high to low pressure. And that's what those diagrams are talking about. So Ryan, you said I've got these two isobars. One's higher pressure, one's lower pressure. Air wants to move that way. toward the lower pressure. But does it? What happens when it tries to move that way?
There's a Coriolis force.
This Coriolis force. Now, all right, let's explain. What do you mean by Coriolis force?
So it's due to the rotation of the Earth.
Okay, beautiful. Because the Earth is rotating, we have this thing called the Coriolis force. What else can you tell me about it? I like that way to start. That seems really basic, right? And do you know what the word basic truly means? Not simple. Basic means foundational, fundamental. So if something's fundamentally, this is what's going on. The Coriolis force is because the Earth spins. And what else can you tell me about it in a more scientific strain? Yeah, Aaron, what do you want to say?
It's an apparent force.
It's an apparent force. And apparent means it's not really there. It just what?
Seems like it's there.
It just seems like it is. And the reason is because we're on that Earth that's spinning around. If we are floating out in outer space, things would be going in straight lines. But we're not in outer space. We're on the Earth that's rotating with it. So we see things and they apparently go to the right. But in real life, the air doesn't turn to the right because of the Coriolis force. And there becomes a balance. That force of the air wanting to go low pressure gets balanced by the Coriolis force. Now, how does the air travel?
Perpendicular, parallel to the isobars.
Okay, it travels parallel to the isobars. We already said it was in a straight line. And it follows what?
Bayes' ballot law.
Okay, so watch this. I have right here an isobaric surface. Okay, and because it's an isobaric surface, I really should be drawing in this, and this would be the what?
Would be the ground.
That's the ground. So I am here. Which way is the air blowing?
I'm sorry, what is the red line again?
The red line is an isobaric surface.
We wouldn't know because we don't have like the directions.
Not the correct answer.
Didn't it move parallel to the red line?
What do you mean parallel to it? Are you saying? I'm not sure what you mean by that. Like if I said, okay, I'll draw an arrow and you want me to draw the arrow parallel to the red line. Are you telling me you want me to draw an arrow that looks like this? Is that what you mean? What if I did it this way?
That would work too.
I mean, that's right. So in other words, Julia, again, this is a conversation. I want to know which way the air is going to flow. And if you'd like, we can pretend this is a marble. Which way does the marble roll?
It roll towards the ground.
Okay. Is that what you're saying? It's going to roll like that? But isn't the marble basically rolling from the right to the left? Isn't it basically rolling this way? And it's basically rolling that way. And what's the pressure here? Higher? Lower? Isn't that traveling from high to low pressure? But really what you just told me is that this marble wants to roll that way. Doesn't it? That's what you've been telling me. But what happens? This is the Earth. Which way does it really roll? If this is analogous to how the Coriolis force plays. Doesn't the marble turn to the right? Which way is to the right? Say it.
Oh,
Are you telling me it turns this way?
so it'd be to the right.
Lena, I'm not sure I knew what you said.
It would turn to the right, or could we say like the opposite of?
You guys, we did this before. Instead of a marble, let's imagine that's you walking on the plane. And I'm walking this way. Which way is to the right if you're walking downhill
Towards the screen.
Oh,
toward the screen? Your wind would be blowing toward the screen. Right? Okay, hold on a second. Let's do this. Let me draw this instead. Which way would this marble want to grow? Or which way is it gonna, it wants to go which way?
Up or down.
But instead, it's going to go into the screen. Okay, if this is the Earth, what do you know about the left side of this diagram and the right side of this diagram based on this picture?
the left side's low pressure and the right side's high pressure.
No, well, no. Yeah, what do you know about this though?
That's colder. The left side's colder. The right side's warmer.
Okay, so if this is the entire northern hemisphere, and this would be the North Pole, and this is the equator, isn't it? So which way does the air want to travel? It wants to travel this way. Okay, think about this for a second. Hold on. The air that's over here starts to move this way. What happens to the amount of air above me? Let me rephrase that. Let me say it again. I'm standing over here and I see the air aloft wanting to go this way.
The pressure decrease.
So there'd be less air above me. So what did the pressure at the ground decrease? Wouldn't this pressure become lower? But the air is going over the North Pole. So what would the air pressure over here start to do at the ground? If this air above me is going over coming toward the North Pole?
It increase.
Which way does the air want to travel down here? From high to low pressure. But if the air is doing this way up here, and the air is doing this way down here, wouldn't the air want to go up? And wouldn't the air want to go back down? And what have I just drawn?
Convection currents.
Which one?
Single celled.
More specific. It's got a
Is
name,
that the Hadley cell?
more specific. Isn't that the global Hadley cell?
Oh yeah.
You remember when we drew the global Hadley cell for the first time? What did we say about the global Hadley cell? What did you write down? Go find your notes on the global Hadley cell.
I have that like the diagram was technically wrong because it was like an oversimplification because that does not take into account the Earth's rotation.
Okay, so that's one thing. Lena, what's the other thing we started with? What was the first thing we said about the global Hadley cell? You should have this in your notes. I know you took it down. I told you to write this down.
Was it the lie that warm air rises and cold air
It's
sinks?
based on the lie that the air that's warm rises. Do you understand? The reason the warm air is rising is because the air aloft is moving. The air aloft, when we drew that first Hadley cell, do you know that the first thing we said is that the warm air rises? But really, what's the first thing that happens is the air goes this way. Then down here, what does the air do in response? Goes the other way, and then we keep the circulation. So the way that this started is that the air moves because there's a what up here? What does this sloped isobaric surface tell me? Direct answer to my question. What does the sloped isobaric surface tell me first? Everybody say, there is a sloped isobaric surface.
There is a sloped isobaric surface.
Right? Do you understand that's what that red line is?
Mhm.
What does that tell me? What is that?
Pressure gradient?
No,
A height gradient.
it's a height gradient, right? The slope of this is, because here, I'm going to do it again, because I've done this once. Slope is rise over run. This is delta Z. This is delta X. That is, the slope is delta Z over delta X. That's a height gradient. That's the slope of the isobaric surface. So I have a height gradient, but what does a height gradient tell me? There's also a what?
Pressure gradients.
There's a pressure gradient. And which way does that air want to travel? This way. From here to there. It wants to go that way. It wants to roll downhill. But now, Lena, what did we say about the Hadley cell? It was a simplification because it doesn't take into account what?
The Earth's rotation.
But the Earth is rotating, and what arises because of it?
Coriolis force.
The Coriolis force. So does the air actually travel from the North Pole to here? No, it starts traveling into the screen aloft. And this is hard because I'm trying to draw in 3 dimensions. Do you agree that, I guess what I could do is, maybe I could try this. I'm actually saying that the air is traveling from outside, maybe this way. Try to see what would make it best. The air is traveling into the board from out of the board, right? It's going in toward the screen. But look at, what does the air want to do down here? It wants to travel from the cold air to the warm air, right? It wants to go from the pole to the equator, but which way does it turn? It turns to the right. Which way is the right down here?
Towards us.
Towards us, out of the board, right? So what's happening is it's going, watch this, into the screen, out of the screen. If this is north, which way is this into the screen? Which way is it traveling?
It's traveling towards the east, but it's westerly winds.
It's a westerly wind traveling to the east. That's where the jet stream is. But we also said that when we spin the Earth, not only do we get a Coriolis force, what else happens to it? When we spin the Earth, what happens to our global happy zone?
Would it stop when it's nighttime because there's no heating?
No. I'm just saying global. Think big time. We said that the global Hadley cell was a simplification because it didn't take into account the Earth's rotation. When I spin the Earth, do you agree I get the Earth's rotation creates this thing called the Coriolis force? But something else happens to this model. What does it become?
Doesn't it become the 3-cell model?
Doesn't it become the 3-cell model? Yes, that's spoken like a question. So don't question, Lena, say it. It becomes a 3-cell model.
It was my Jeopardy answer.
Right? So we get a 3-cell model. But here's the thing. It comes about because the Earth is rotating. And so what does the air travel? It wants to travel in toward the low pressure, which is, it wants to travel toward this way. It wants to travel this way, but instead of going that way, it travels into the board. In other words, if there's a marble here, does this marble roll down the hill? No, it blows along the hill. All right, let's try this. What does this mean? And I'm going to make it real simple. What does this actually look like if this is a mapped down view of an isobaric surface? Describe what this would look like in real space.
So the pressure is going to be the same in the entire area. So the weight of the air in that entire area is going to be the same in any place in this area.
You were breaking up a little bit on me. I want you to see if you can describe this.
Would it be like a dome?
Would it be a dome? Do you guys understand what Zach is saying? You think it would be a dome?
Like, if we looked at it from like if we take from one end of the circle to the other end of the circle and we look at it on a flat plane, would it be like kind of like a parabola, like a circular shape?
Well, hold on a second. Think about this. Remember, is this an isobar or an isoheight?
That would be iso height.
Okay, this is an isoheight, right? So what am I doing when I go in toward the center? If I'm walking here to here to here to here, what am I doing?
Are you increasing in height?
Isn't this low? Low pressure is low heights.
Oh, yeah.
So imagine that I had a tarp stretched across the room. That's 500 millibars. Every place on the tarp is 500 millibars of air pressure above it. This is similar to putting a bowling ball in the middle of it. If I put a bowling ball in the middle of that tarp, what would that tarp do? Wouldn't it go down in the middle? It would go down both ways. So this is in 3 dimensions looks like this from the cross section. Why does it do this in the atmosphere? Do you understand this is the cross section, 500 millibars? I don't know if you understand this when I say, do you understand this? But I'm really needing you to answer me. Do you understand it looks like this? So Zach had originally thought a dome, but you understand you were backwards.
Yeah, I was looking at the surface.
It's like a valley or something. Okay. What would cause this? Why does it
Would there be
pivot down, cave down?
Would there be like a pocket of cold air there?
Aren't we saying that the air is cold? So if I have a map with a big circular area, what I'm really saying is the average temperature in that is cold. Now let's think about this. Over here, if I put a marble, what would the marble want to do?
Would want to go down towards the cold or to the low
We
pressure.
want to go down here, right? The marble wants to do that. If I put a marble here, what would it want to do? Go down. If I put it, but you agree that this goes in and out of the board as well? So watch this. Imagine that I put a marble here, 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 and here. What would all those marbles want to do?
Go towards the center.
Do you agree that they'd all want to converge toward the center like this? Are you following that, guys? Nod your head, or it all wants to go that way. But the Earth is spinning, so what does it do?
Deflects to the right.
So it wants to go this way, but it turns to the right. It wants to go this way, but it turns to the right. It wants to go this way, but it turns to the right. It wants to go this way, but it turns to the right. So which way is the air going to eventually be going?
Anticyclone.
No. It's going
Cyclone.
counterclockwise, which is cyclonic.
Yeah.
So do you understand the marbles are not traveling toward low pressure? They sort of spin around this divot in the tarp. The only difference between this and what's really happening in the atmosphere is this. Okay, so watch this. Hopefully I can draw this for you. Here's a plane. And then I put cold air in the middle and it creates this divot. But one side is closer to the equator, the other side is closer to the pole. So rather than being a divot like this, the divot is actually more like this. It's actually a sloped divot. So that The North Pole side, this is way closer to the ground than this side is. Okay, now watch this. Do you see this big circle here? I'm going to have to erase this. I have an area of low pressure here. Look at the winds going around it like this. And up here, I've got airflow, and up to the north, again, now you're going to have to look at this, Kevin. This is 5,340 meters above sea level. This is 5,820 meters above sea level. But so it's a divot, it's a big circular thing, and to the north it's sloped down closer. But now, you ready? Watch something really cool. Watch what happens when, instead of showing you the wind speeds, I show you the temperature. What do you expect? Where is the cold air going to be?
In that pocket.
These are the temperatures. Pinks are in the negative teens, the grays are in the negative 20s. You see that we've got a pocket of cold air right there, right in the middle of that low. And where else is it getting colder? Way to the north by the pole. So this vortex is entrenched in cold air. Remember a couple years ago we had the polar vortex? The polar vortex is because we had an area of low pressure, so we know which way the winds are flowing, but it was a cold pocket of air. That's the polar vortex. You guys remember the polar vortex?
Yeah.
So watch what happens as we move forward into time. Do you see cold air coming in? See what the temperature at 500 millibars right now is negative 15. Over here, the temperatures in gray are negative 24. So right there in Chicago, it's negative, let's say negative 14. We go forward into time. And what's the temperature now? Negative 15. A little bit further in time, the temperature is now negative 20. Cold air is coming in. That's higher up in the atmosphere. But over here, how high above the ground do we have to go to get to 5,700? I mean, to get to 500 millibars, 5,700 meters. Over here, when there's colder air, I now have to go only 5,614, 15 meters to get to 500 millibars. That's what the atmosphere is. So if I were to go up to, let's say, even jet stream level, and let me make it a little bit bigger. Oh, I know what the problem is. You see that I have a jet stream that travels this way. You know what? Let me do it this way. The jet stream does this. It makes a wave. Do you agree that in this part of the wave, what's happening? Which way is it curving?
It's like cyclonically.
Cyclonically, that's a trough. And what's it doing over here? Anticyclonic, and we said that's a ridge. Do you see that it's making a wave?
Mhm.
With your hand, show me the wave with your right arm. Okay, you are all wrong. And I'll tell you why. What you're saying is that the air is going up and down. Isn't that what this looks like my arm's doing? It's going up and down. Which way is the air traveling? Do you understand that the air travels parallel to the isobars? But in this case, it's traveling parallel to the isoheights. So the air is doing this. It's all traveling at the same height. It's not going up and down. It's traveling at the same height, snaking north and south. So over here, the air is traveling to the southeast. Where did you go? Oops. Hold on, I lost your faces. Where are you? Oh, here. I hate when this happens. There we go. Oh, there you go. You did, I don't know what, I had a button accidentally and you disappeared on me. Okay, so over here, the air is traveling to the southeast. Here it's traveling to the northeast. Here it's traveling back to the southeast. It's making these waves that are actually this way. And that's the jet stream. That's how it's traveling. So given this, or given this, I would see the strongest winds, in this case in the color reds, where I've got the strongest gradient, height gradients, pressure gradients. But why do I have the gradients? Because I have changes in temperature. That's the thermal wind. So these things are, look at this big thing up here. Look at the wind speed. Do you see that the wind up here is traveling this way? It's an upper level area of low pressure. That's what we call it, an upper level low. And the wind's traveling cyclonically. But what is that low? That's a vortex. What is it really? The vortex is a result of strong cold air that's in place right over there. In fact, look at the temperatures. Temperatures are 44 degrees Celsius below zero at 5 kilometers above the ground. That's really cold air. So when I see a jet stream, that looks like this. I'd say, what is this section? This is a trough because the air is curving cyclonically. What's it doing here? That's a ridge because it's curving anticyclonically. And this is a trough because the air is curving cyclonically. But let me warn you, boys and girls, what is the air doing from there to there? Do you agree that in that part of the wave, the air is actually traveling fairly straight? And from there to there, the air is traveling very straight. Which means that in this area, these winds are actually what?
Geostrophic.
Geostrophic. Or the way that I used notation last week, I say that the actual wind is what I would expect it to be given the geostrophic equation that I could solve for how fast the winds are. Negative 1 over rho dp dx equals 2 omega v sine phi, solve for v. In the trough, though, what is the air going to be? Where it's curved cyclonically, what do we know about the wind?
Would that be the subgeostrophic?
Right? The actual wind speed is less than I'd expect given the pressure gradient, subgeostrophic. What's it going to be over here?
Supergeostrophic.
Supergeostrophic. And then back to subgeostrophic. So let's just imagine that every place on this wave is the same pressure gradient. What would the air be doing? It's slow here, right? And then what does it do here?
Speeds up
It speeds up. When does it go fastest?
at the peak,
At the peak. Then what does it do here?
slows down.
So, doing the wave with both hands. Show me what's happening when the air speeds up. So make one hand go right behind another hand. Don't make it like this. Make it so like it's two cars in a row on a road. What happens when they come out of the trough?
They speed up.
So is that what you're going to do? Which car speeds up first, Zach?
The first car and the second car follows.
So if the cars were going like this, so watch this. If the cars were here and here, when they come here, who's going to go first? Won't the first car go fastest? And what's happening to the spacing of the cars?
They get larger.
So what is the air doing?
It's
Isn't that divergence there? They're spacing out, right? Imagine that you were driving on a road that looked like this, and there's a cop sitting here in the trough.
Mhm.
Soon as you go past the cop, what happens to the traffic? Everything speeds up and it spreads out again. Okay, and there's a cop over here. So what's going to happen before you get to the cop? What happens to the cars here?
slow down.
So what's going to happen over in this area?
A convergence.
Isn't that going to be convergence? Now, here's the deal, guys. If I said in the upper atmosphere, show me divergence, what you probably would have done is done this. Divergence is flowing in different directions. But do you understand here which way is divergence happening? Going in the same direction. So the air is doing this and spreading out. Okay. It's hard on camera. It's so much more fun when we're in the classroom and we can do this. But it's spreading out like this. It's going in the same way. Do you understand that's still diverging? And then you go over the ridge, and then what happens to the spacing of your hands? It gets closer together. So it converges. This is happening where, though? Where is the jet stream? Isn't it upper level? So in this big circle here, in white, the air is converging. What does that mean? Based on mass continuity.
Would there be a higher pressure?
Which means which way is the air traveling? The air sinking? If it's convergent aloft, doesn't that force the air to go down? And what's happening in this other circle?
Rising.
So when I see a jet stream like this, where is the air rising? How would you describe in words where the air is rising, where the divergence exists? Oops. Where is that divergence occurring? Can you read that? This is occurs, Kevin.
Yeah,
Divergence occurs where?
Between when the air is moving between a trough and a ridge.
Okay, so what I will do, that's right, Zach. Divergence occurs. I'm going to say downwind of an upper level trough. That's what I need to think about. In fact, in all of meteorology, I always think about where it is with respect to the trough. If this is the trough, that's downwind. Okay? Let me show you something. So where would convergence be?
Downwind of an upper level ridge.
Right, you could say that and I would be fine, but really everything's based on the trough.
Upwind of a
So
upper
upwind
level.
of an upper level trough. So this is all upper level. Now, Zach, you were even more right. This is where high pressure exists at the surface. This is where low pressure exists at the surface. Watch this. I've got this map. Do you agree? Well, hold on, I'm gonna have to erase this. I've got an upper level low and a trough here. And there's the ridge. Where's the air going to be rising? In this area. Here's where I'm expecting severe thunderstorms today. Isn't that the region downwind of that upper level trough? So Lena, you especially, because you take in severe weather, we know that we want rising air destabilizes, all sorts of stuff. We did this in outlines, but we didn't really talk about it because I can't do everything. But now do you understand that when I have this upper level trough, this is where I expect there to be thunderstorms?
Yeah, I had no clue with that.
So because it's downwind of the upper trough. And if you go back to your notes, you will find some of that stuff in there, but we just didn't have time to get into the details of it because you have to put those two together.
Okay.
So that's what we'd expect to be going on. And it appears as though
So do we have a chance for
right now, look at
thunderstorms?
this. There's a tornado warning right over here. Let me show you. Let me show you what storms there is. There's, hey, Lena, you remember what this is right here?
Where were we looking?
It's a 3-body scatter spike, big time.
Oh yeah.
That is a nasty looking stuff. So there's a tornado warning.
Wow.
Wow, that's a big storm. Now I started the day virtually chasing here. I was going to go up to Childress, which is here, and I started in Abilene. So I would have probably come down and just been right there. Would have been easy to catch this one. Velocity. Oh yeah, look at this thing rotate there. Ooh. Okay, so warning stash. Let me check on something. Radar indicated a tornado. Tornado and 2-inch diameter hail. That's good size hail. And yet they only have a severe thunderstorm watch. So let me show you this. Wait, what do I want? I want this. Convective. We're almost there. Convective watches. So here, there is a tornado watch. I mean, that's a severe thunderstorm watch. Probability of 2 more tornadoes is 20%. So there's a few tornadoes, and I think it says that here. a tornado or two is possible. And hail to 2.5 inches. So if you kind of take a look at this pattern, that is what we have today. That's why we're working this stuff. That was a pretty intense lecture today. What do you think?
Mhm.
Mhm.
How well did you understand it?
I think I'm at like a 4.5 maybe.
I'm getting a couple of 3s, a little bit lower on this one. I would suggest, Ryan, where are you at?
Yeah, 3. I'll probably have to rewatch now.
Aaron, how about you?
She says 3.
3. Okay, so this one I would go back. Now, what we need to do is we're going to go back and get where the highs and the lows are, because we need to talk about what happens to the ground. We're going to see how all of this goes together. So I wanted to finish this to re-talk about it, but I definitely think you need to spend the time on the notes before Thursday's class. Other than that, there's no lab. I'm not giving you any other assignment. Just for now, you got to kind of review this. This is kind of meaty stuff, but this is really what weather is all about. Isn't it kind of fun? I mean, it's like, this is intense stuff, but now you understand what weather is. So when people say things about, oh, meteorologists never get things right, yeah, they're full of it. It's a very difficult thing to do. You know why? We're predicting the future. You ever tried to predict the future? Yeah, you should try. Okay? Anyway, so go through this, get your notes really good. This is going to be super important that you get a really good set of notes on this. So I would work that up, okay? Everybody okay with that?
Yep.
You know, you just finish your test and we'll talk about stuff. We're going to have some fun lectures and then we'll start putting it all together into really how the weather works. Okay, guys, we'll see you on Thursday.
Okay.
Thank you.
Bye.
Bye.